Ready? Okay, we were doing gaseous state last time, and in gaseous state today we'll be taking one step higher. Uh, Last time we finally derived the ideal gas law equation. What was that? PV is equal to nRT. Alright, and when we do the PV is equal to nRT, now I told you whatever we had done last time can be quickly recapitulated from this particular equation expression directly itself. Alright, now you know that there are some laws which are followed by ideal gases. There are some gases which follow Charles' law, Boyle's law, and those are known as the ideal gases, right? And Charles is colorful. So in Charles, according to Charles' law, we had actually put a constant pressure, and your amount was fixed in all of these. In constant pressure for Charles' law, and when we say constant pressure means, you know, this is like already a constant. If you taking it for a fixed amount of gas, say 1 mole, so then in that case you know that your volume will be directly proportional to temperature. And here itself remember that this means that our V by T is a constant. So you will get direct numericals which we haven't taken up yet. It is just like direct application. You will be given initial volume, final volume, initial temperature, and not the final temperature. And then you can easily substitute the values as V1 by T1 is equal to V2 by T2, and you can easily find out T2, T1, whatever is asked. Okay, so then after that we also started up with, this was the first one in fact which we did. In Boyle's law we have a constant temperature and fixed amount of gas. In fixed amount of gas, in this case we have constant temperature. For constant temperature what we have is pressure is inversely proportional to volume, because Nr is already a constant, you know, here, and temperature is a constant, so your V can be taken to the other side, or you can say your PV is a constant. So one important relationship comes, because from your numerical point of view you can be given the initial values and the final values. So you have to remember that P1 V1 is equal to P2 V2. So whatever is given in the question, you can just have a look at it and decide accordingly as to what is to be substituted where. Then we after that talked about the Gay-Lussac's law of constant volumes. In Gay-Lussac's law what we have is, you have constant volume. So in constant volume means what? Now your pressure will be directly proportional to temperature. So here you have P by T is a constant, and the relationship from your numerical point of view will be P1 by T1 is equal to P2 by T2, as simple as that. Alright, and then you have Avogadro's law, which states that under similar conditions of temperature and pressure, what we basically have is equal volumes of all the gases will have equal number of molecules. So basically we state from here that if your temperature and pressure are now constant, then in that case your volume is directly proportional to N. Then just at the end of the class we discussed our Graham's law of diffusion also. What was Graham's law of diffusion? R1 upon R2 is equal to under root of, and it can also be related to your molar masses also, and alright, and then you can also, there was one topic that was left, that was Dalton's law of partial pressure. So we'll just quickly go through it. Remember that all those gases which follow Charles' law, Boyle's law, all these laws under all conditions of temperature and pressure are known as ideal gases. Generally whatever gases you are having are way off from the ideal behavior, and if at all they will behave ideally, that will be at low pressures and high temperatures. Alright, that will be at low pressures and high temperatures. Then we quickly discuss the Dalton's law of partial pressure. It just states that the total pressure exerted by a mixture of gases, non-reactive gases, Dalton's law of partial pressure states that the total pressure that is exerted by a mixture of non-reactive gases is equal to the total pressure exerted by a mixture of non-reactive gases is equal to the sum of partial pressures of individual gases. So that is equal to P total is equal to P1 plus P2 and so on. So this is what your Dalton's law is all about. Now you know that what is your P1 equal to? Your P1 is equal to, if it is for it is the partial pressure of course, and it is like the individual pressure that is exerted by that particular gas. Now according to ideal gas law equation, you can always put it as what is your P, that is equal to nRT by V. Alright, so then in that case, if I am talking about say a constant volume of the container and at a particular temperature, in that case my P1 will be, say what is my P1, that will be equal to N1 RT by V. Any doubts? No. So then in that case, for each one I can have a similar representation for P1, P2, P3 and so on. So there I will have P total will be equal to, that will be equal to N1 RT by V plus N2 RT by V plus N3 RT by V and so on. Okay, and if I take the ratio of say P1 by P total, what will that be equal to? Your RT by V and RT by V will cancel out each other. I will have P1 is equal to nRT by V and P total is N1 RT by V plus N2 RT by V and so on. So when I take the ratio of this expression upon this expression, then that will be equal to nothing but N1 upon N1 plus N2 plus N3 and so on till the total number of gases that you have. Remember that all these gases are non-reactive. So that is your total this thing expression that is coming out to be. And what is this N1 upon the total number of moles? It is the mole fraction of component gas number 1. So then in that case your P1 will be equal to mole fraction of 1 into P total. This is one of the expressions that is like a consequence of your Dalton's law of partial pressures. Dalton's law of partial pressure, what does it state? Dalton's law of partial pressure states that the total pressure exerted by a mixture of gases is equal to sum of the individual partial pressures of each of the gas. Alright, P1 is equal to N1 RT by V because we are assuming each of the gases to be an ideal gas, and then we just substitute each of the P1, P2, P3 the partial pressures according to that. We've just taken up the ratio and we found up a relationship for P1 is equal to chi1 into P total, where chi1 is the mole fraction. So then if I generalize this expression for P2 also, this can be done. What will it be for P2? P2 will be equal to N2 upon N1 plus N2 plus N3 and so on. So that will be chi2 into P total. So whatever we have is like, it can be generalized as P ith. If we talk about the ith gas, that will be equal to the mole fraction of the ith gas into the P total. Similarly, you can also derive an expression for volume as well. Had you done it for volume at a particular pressure, then in that case your volume can also sum up to the same. The total volume will be equal to the sum of the individual volumes of all the gases. Alright, and then that volume, I am not doing it for you, you can just understand it. What it will be of V1, it will be N1 RT by P1. So similar, or following the similar steps, what will you get is, you will get V1 to be equal to chi1 into V total. Alright, and this is something which is known as the Amagat's law. Amagat, A-M-A-G-A-T, named after the scientist only, so can't be helped. So Amagat's law of constant, Amagat's law of volumes. So where you have V1 to be equal to, and it is like a consequence of your Dalton's law only. Because we used the Dalton's law, we substituted the values there and then we finally arrived at this expression. Okay, there is another way. Normally, see, whenever gases are collected from over the, they are never dry, they are always in the moist form, because normally gases have a good amount of pressure over the over the wet areas. So normally gases are collected from there. So if at all you have to find out the pressure of a dry gas, remember that pressure will be equal to the total pressure of the gas minus a factor called aqueous tension. Okay, and what is that aqueous tension? It is nothing but the pressure exerted by saturated vapor, water vapor. Okay, I am talking about how to find out the pressure, because there are questions based on it, and it is like a very simple concept even given in NCERT, I suppose. So there what you have is, you have the pressure of the dry gas. Remember this, the pressure of the dry gas, it's like a very simple kind of a stuff. You have pressure of a dry gas to be equal to the pressure of the gas, the normal pressure of the gas, minus the aqueous tension. This aqueous tension is nothing but it is the pressure exerted by saturated water vapor. Aqueous tension is the pressure exerted by saturated water vapor. Okay? With this we've, I mean, by and large covered. Last time Dalton's law was like left because we went into details with the plots and other things. So I hope all of you all are now clear with the plots. So now if I actually talk about, yes, yes, normally one good thing about chemistry is like you will be provided with all the values, you just have to, and if at all, if it is, it will be like an application of one step higher. So a little bit of common sense along with your mind is like required. So if you, okay, so pressure of the dry gas is equal to the pressure of the gas. I mean, the law, that's the new law that we've done today, is only the Dalton's law of partial pressure, and it is like the total pressure is equal to the sum of the individual partial pressures of each of the gas components. Remember that these gases are not interacting. This is an assumption. ऐसा होता तो नहीं है in reality. This is only an assumption. If you have gases in the atmosphere, they're constantly interacting with one another. But it is only an assumption for the ideal behavior that they're not disturbing any other gas molecule. But in reality, they are interacting. That is why we have deviations from the ideal behavior. So after that, what did we do? Just a quick recap of the three formulas, simple formula that we done. The total pressure is equal to P1 plus P2 plus P3 and so on. Alright, from there we get P1 in terms of P total as P1 is equal to Chi1 into P total. What about V? Same. V1 is equal to Chi1 into V total. Alright, and then the pressure of the dry gas, which is total gas pressure, gaseous pressure minus the aqueous tension. What is aqueous tension? Pressure exerted by saturated water vapor. Brilliant. Okay, so now we start out with a new concept, which is the kinetic theory of gases. Kinetic theory of gases, this is actually, see, theory is some kind of a set of laws which is generally like, law is like, it is derived after some kind of experimentation. Difference pata hona chahiye na, what is the difference between a theory, what is a postulate, what is a hypothesis. So normally a theory is something which is given to start up with the base. तो उसके अंदर कुछ हमें postulates या assumptions लेके चलना पड़ता है. And what are postulates? Postulates are something जिसका कोई derivation नहीं है. This I told you when we did Schrodinger wave equation. Okay. So kinetic theory of gases has, it is a theory which was especially given based on certain postulates. What are those postulates? I will quickly discuss, and they talk about the interaction of the gaseous molecules. इसी को use करके then we actually tried and studied the properties of gases, which is our main focus. We will talk about this. This is what our class, today's class is all about. We will talk about as to why real gases behave ideally at low pressures and high temperatures. Now this is the base. So your answer will take the entire class. So kinetic theory of gases, the very first assumption is like, we have the gas comprising of small particles which are identical in size and shape, alright, which are known as molecules. So what we have is, the very first one is like, your gas comprises of small similar sized sized and shaped molecules, small similar in sized and shaped particles which are known as molecules. Alright, this is the first postulate. Then the second postulate is that, remember that the volume of each of the gas molecules is each of the gas molecule, that means the volume of one gaseous molecule is negligible in comparison to the total. We assume that the total volume of the gas will be like something, what do we say, the volume of the gas may be the volume of the container in which we are putting it, because it takes up the shape and the available space. So what we have is volume of the gaseous molecule, the volume of one gas molecule is considered to be negligible in comparison to the total volume of the gas. Alright, then the next postulate is that the molecules are assumed to be in rapid motion, which is completely random. Rapid motion means very fast motion, which is completely random, matlab koi it is not following any set pattern. They are just moving in any direction the way they want to. Alright, I repeat it again. In kinetic theory of gases, the third postulate that I am talking about is like molecules are rapid in motion, which is completely random, means they are just moving the way they want to. So, ये सब करते time they are colliding with one another, and also they are colliding with one another, and they are also colliding with the walls of the container. The point here is not, that is the next postulate. The point here is that I have already told you last time that remember, whenever the gas molecules collide with the walls of the container, they exert pressure. Alright, so pressure is due to the collision of the molecules with the walls of the container. And we are assuming here in this case that the molecules are perfectly elastic. The molecular motion is like perfectly elastic. What do you mean by elastic motion? That there is no gain or loss of energy. So we are assuming that molecules are perfectly elastic. They are perfectly elastic. And then remember, following the laws of classical mechanics. Remember, when I talk of classical mechanics, you know they are the study of macroscopic objects. So what you have is law of classical mechanics agar hai, to classical mechanics basically talks about the Newton's law of motion. Whenever we talk about quantum mechanics, that talks about the Planck's and other laws. So basically here the laws of classical mechanics, especially the second law. What is the second law of Newton's second law? F is equal to ma. So what you have in particular, the second law of motion is like applicable to molecules in motion. Then there is no force of attraction or repulsion between the molecules. There is no force of attraction or repulsion between the molecules. Okay, there is no force of attraction or repulsion between the molecules. And the last point is that at any instant a given molecule, at any instant a given molecule can have energy ranging from a small to a higher value, can have energy ranging from small to any high value. This is what our second part of today's like meant about Maxwellian's energy and velocity distributions, small to high values. Alright, let's go through the postulates once again. What are we doing? Kinetic theory of gases. It is mainly focusing on our ideal gas behavior, right? Now the very first thing is like we are assuming that our gas has small identical particles which are known as molecules, with their identical in size and shape. First thing. Second, the volume of the gas is negligible in comparison to the total volume. Then the third, molecules are in rapid motion. They are colliding with one another also and with the walls of the container. That you understand very well. Then they are perfectly elastic motion. Then fifth, no forces of attraction or repulsion, matlab they are not interacting with one another at all. That is why when we do the Dalton's law also we state that it is for a mixture of non-reactive gases. They like not interacting with one another. And then the last one, at any instant a molecule can have energy ranging from a small to a higher value. Why do we say this? इसको मैं हल्का सा explain कर देती हूँ. जैसे for example, if our molecules of the gas are moving in a container, you know that they are constantly changing their speed, they are colliding with one another off and on again. If they will collide with one another, then unka velocity will also keep changing, and if the velocity will keep changing, then their energy also keeps changing. So we do not talk of any particular energy being possessed by a molecule, but rather we say that the energy resides within a particular range. Okay? Like we cannot say that this is a particular molecule which moves with this speed. Okay? तो उस केस में even for speed we can talk about a range of speeds. That is what our Maxwell's relation is all about. Now here in this case, when we are saying the molecules are perfectly elastic, we are also relating it to the type of energy. If you say there is no loss or gain of energy, but when we are talking about the motion is like kind of random. So we are saying that if we are talking about the energy in reality would be like of two types. This is like an assumption which will actually be proved later. Where is it? The perfect elastic. It is like an assumption which will later be now proved that your ideal gas law equation is not applicable to the real gases. Okay? So now the overall energy remains the same, but even for if you're saying elastic motion, she is absolutely right that if you're talking about the collision, then in that case there should be no loss or gain of energy. That I hold back again. So this range of energy refers to the real kind of a behavior, which is like putting it some kind of a creepance of the real behavior. Now what we have is all these points are important. Out of these points, please remember this point and this point especially. Alright. Point number 2, which says that the volume of the gas is negligible in comparison to the total volume of the gas, and point number 6 on the board where it says that there is no forces of attraction or repulsion. Okay? Is that clear? These are like the postulates of kinetic theory of gases. Now based on this postulate, we actually talk about a derivation of the kinetic equation of state, a kinetic gas equation. Just as you had an ideal gas law equation, what was that? That was equal to PV is equal to nRT. Now similarly you get, the derivation is not there in your course, so I am not going into the details. So here what you are talking about, basically you are talking about a gas molecule moving within a container in all the 3 spatial dimensions. In all the 3 spatial dimensions, alright. So here say this is ux, this is uy, this is uz. So the total speed will be like an average of, it will be like under root of this will be an average of ux square plus uy square plus uz square. Just understand this. And the total equation in this case turns out to be equal to, please note down the kinetic gas equation which comes after, explain 5 number point again. Alright. The 5th point states that it adheres to the laws of motion. Classical mechanics means whatever laws are applicable to the macroscopic objects are all applicable to these molecules. Let me tell you, when we move on to the kinetic theory of gases, we are talking about the atomic particles or the molecules of gases in totality. So that are actually microscopic. But in this postulate, what are we making an assumption? We are making an assumption that they follow the laws of classical mechanics. That means the Newton's laws of motion, the first, second and third law are applicable to all these molecules. So one kind of a deviation which should not be ideally followed, because when you talk about gas molecules, you are talking about microscopic entities, but here you are talking about the laws of classical mechanics to be applicable. And why are we talking, then why are we talking when we know gas molecules are microscopic? These are only a basis of the theory which were set initially to come and derive a relationship for the ideal gas behavior. Okay. So now after this, revise the postulates again, because each of these postulates are important for you. There are like simple ones, but point number 2 and point number 6 are to be remembered. What were those 2 points? One was that the volume of the gas is negligible, and the second is that no force of attraction and repulsion. And by and large, you know that the molecules are moving under elastic motion, and laws of classical mechanics will now be remembered because it came as a doubt, and you know each of the molecules are identical in shape and size. So essentially 5 are these, 5 of them are these, alright. Then I am putting down now the kinetic gas equation. Based on these postulates and these assumptions, we have the kinetic gas equation, and your kinetic gas equation is equal to PV is equal to 1 by 3 mn u bar square, alright. And remember here that here P is the pressure of the gas, V is the volume, your M stands for the M stands for the molecule, the mass of each molecule, and you have N as the total number of molecules which are there, and your U bar square is nothing but it's your root mean square speed, which is like U bar square can be now put as 3 PV upon mn. This is your root mean square speed. Why is it the root mean square speed? Because I told you that this U bar square is nothing but equal to your ux square plus uy square plus uz square, and it's taking the average, not the average, but rather it is like a combination of all the speeds in all the 3 dimensions, right. So you have your U RMS square to be equal to 3 PV by Mn. From here you can remember that, and this is derived from, this is like taken up from your kinetic gas equation only. This kinetic gas equation, let me tell you, is similar to your ideal gas equation. This is also again something which is followed by all ideal gases. How can we talk about that? See, in this case, here remember that your average kinetic energy, another important factor, your average kinetic energy will be directly proportional to temperature. Are you all here with me? What is your kinetic energy? Kinetic energy refers to the motion of the molecules. If I increase the temperature, then the motion will increase, and then naturally your average kinetic energy will also increase. What is your, so that means your average kinetic energy will be equal to your average kinetic energy will be equal to some kind of a constant into T, some constant K into T. And what is your average kinetic energy? Generally it is half m into, here I am taking the root mean square to be as u bar, so let that be u bar only. So half mu square will be equal to your kT. Okay. Now this is your 1 by 3 mn u square. So if I substitute u bar square here, from here, then what will I get? I can pick up u bar square from here and substitute it back in this expression of the kinetic gas equation. So then in that case I will get my PV to be equal to 2 by 3, you can check it for yourself, it will be equal to, you can just put half mu bar square and then just check it out and just multiply, and so that will be equal to 2 by 3 into n into half mu bar square. I am just substituting my, the kT is to be substituted, no. So you can just check up, this will turn out to be equal to 2 by 3 n kT. Just check it out, u bar square will be equal to, it will be 2 kT by m, right? And you just substitute your 2 kT by m here directly, right? Here with me? So here what do I get? Again a relationship which has been arrived at from my kinetic equation of gas. Now what were the laws which were followed by the our ideal gases? They were like the Boyle's law, Charles, Gay-Lussac. Let's check 2 and 3 and then we'll say it follows. Alright, Gay-Lussac's law. Now let's check it out. Boyle's law states that at constant temperature, just look at this, at constant temperature, this is the total number of molecules, K is a constant, 2 by 3 is a constant. So at constant temperature your PV will be a constant. So Boyle's law is being followed. At constant pressure your volume is directly proportional to T. At constant volume, what you have, pressure is directly proportional to temperature. And if you check up, at constant pressure and temperature, equal number of volume will comprise of equal volume of different gases will have equal number of molecules. This is your Avogadro's law. So all the laws are actually being followed from here as well, and this is your kinetic gas equation. Alright, this is different from your ideal gas equation, but remember this. Another thing that you can just write down, remember here itself, look up onto the board. This is your root mean square speed. Root mean square speed, PV is equal to nRT, you know that. If I talk about 1 mole, then in that case, what is this small, if it is the mass of one molecule I stated, and if n is the total number of molecules. If this n is Avogadro's number for 1 mole, देखो PV is equal to nRT. If I am taking n to be 1, I am talking about 1 mole only. और एक mole में कितने numbers होते हैं? Number. That is Avogadro's number. So that means the total number of molecules will be Na, and mass of one molecule into Avogadro's number will be your molar mass. Alright, and this can be written as 3 PV by m also, and which can also be written as 3 RT by m also. So this expression should be remembered for the root mean square velocity, root mean square speed. So here your root mean square speed is equal to 3 PV by m, which is also equal to 3 RT by m. And also from here I can write down that my kinetic energy is equal to half m u bar square. And what is your u bar square now? That is equal to 3 PV by mNA, right? That is equal to 3 PV by mNA. So I can also write it as 3 by 2 PV by n. Alright, I can write it as 3 by 2 PV by n, which can also be written as 3 by 2 RT by Na. If I am taking the number of moles to be equal to 1, your n becomes automatically Na. Alright, and you know that your R by Na is nothing but, that's your Boltzmann constant. So it can also be written as 3 by 2 kT. From where you get that, the average kinetic energy is directly proportional to temperature. So you have back calculated it also. I'll just quickly revise it all so that you do not get confused. Right? Now we have now started out with kinetic gas equation, and in our kinetic gas equation we have certain set of postulates, out of which there are some 2 or 3 which are more important to be remembered, because then on the basis of that we will come to the equation for the real gases also. One of the important assumptions was like that the volume of the gas is negligible in comparison to the total volume. Next we stated that there is no interaction, no force of attraction or repulsion between the two. Alright, and the rest are also can be remembered, that there is elastic motion, and then the energy is like variable. It ranges from a small to it can go to any high value in totality also, and then there are other postulates. Okay, so from there, based on those postulates, we get another equation which is applicable for the ideal gases. And why do we say ideal gases? Because we are saying they are not interacting. So that equation is nothing but PV is equal to 1 by 3 mNu square, where m, small m, is the mass of one molecule. Remember, whenever you are writing an expression, be clear about each and every term that you are writing. So this is the mass of one molecule, not simply the mass of any total gas. N is the total number of molecules. Your u bar square is the root mean square speed. Root means it will become the root when you put a root. So u bar is your root mean square speed. Otherwise you have u bar square here. It is the mean square speed. Otherwise, when you put a root here, when does it become RMS? When I put a root here and a root here. So now this is your u bar, which is RMS. Root mean square speed. Okay? And that is equal to, simply from the kinetic gas equation, that is equal to 3 PV by Mn. ये तो हमारी kinetic gas equation से ही आ गया, PV is equal to 1 by 3 MNU square. Alright, so URMS will be equal to, URMS whole square is equal to 3 PV by Mn. Now when I am using the equation of ideal gas law, which I have already done, there I know PV is equal to nRT. I can take n to be equal to 1 mole, and whenever I take 1 mole, my number of molecules become equal to the Avogadro's number. So that becomes m into Na, when as soon as I substitute it with RT. So that becomes equal to 3 PV by capital M, which is the molar mass now. Capital M is the molar mass of the gas that you are talking about. That now PV can be straight away replaced by RT. So 3 RT by M. Alright, this was one aspect that we have done. Two important expressions that are to be remembered here is one, what is the kinetic gas equation? PV is equal to 1 by 3 MNU bar square. And what is your URMS? That is equal to 3 RT by M or 3 PV by M. Please remember this root mean square speed. Then here we also stated that PV is equal to 1 by 3 MNU square. So I can actually talk about this half MU, or I can replace this MU bar square from my kinetic energy relation with temperature. I know that my average kinetic energy is directly proportional to temperature, and I know kinetic energy is equal to half mu bar square, that's half m into velocity square, that will be equal to kT. Using this expression we get another expression, that is PV is equal to 2 by 3 nKT, where K is just a simple constant. Alright, and here we can then apply the different rules and just check it up that even this is followed by all ideal gases. Done. Next, after that, what we have is that we have kinetic energy is equal to half mu bar square, and I now know that I can replace my u bar square from my kinetic gas equation. This is like a long derivation that I will pass on it to you just after the class, and it can be mailed by the coordinator. Alright, it is like a 3 pages long derivation which will take about 1 hour's time to derive. The derivation is not there in your course, but definitely you can just refer to the book that I have and I will just pass it on to you. Okay, so now here what we have is that the average kinetic energy is directly proportional to temperature. This is all done. Kinetic energy is equal to 1 by 2 mu bar square. We are now replacing our u bars from the kinetic gas equation, and when we substitute it we get an expression that our kinetic energy is also equal to 3 by 2 PV by N, and that is also equal to 3 by 2 RT by NA, or 3 by 2 KT. So done with this, then we move on to the next aspect of it. And again, this is a law which is followed only by ideal gases. Remember that if we are talking about some kind of a deviation from the ideal behavior, then what are we talking about? We will be talking of a compression factor or a compressibility factor. Alright, this compressibility factor is nothing but yours given by Z, which is ideally equal to the volume of the gas, observed volume of the gas upon the volume of the gas had it been ideal. So we talk about Vm observed upon Vm ideal. This is an important aspect because we've been constantly talking about, say, ideal behavior, but in reality we do not get the same kind of a behavior amongst the gases. Why do we say that? Because, say, when we are talking about no forces of attraction or repulsion, agar there is, if at all there is no force of attraction between the gas molecules, then in that case your gases would never liquefy at all. If we talk about gas molecules and if there were no forces of attraction, they would never come close to one another, because in order to liquefy you need to have some kind of forces of attraction. They would never liquefy or they would never solidify. So that is why there is a need to understand it even better. So here what we have is that we talk about a deviation from the ideal behavior that can be given in terms of a compressibility factor or a compression factor. And what is that? It is the ratio of the observed volume upon the ratio of the volume of the ideal gas. Alright, and you know that what is your ideal gas? It follows the ideal gas equation, that is equal to PV is equal to nRT. So your V will be equal to RT by P. So this can be given as, I am replacing this Vm for 1 mole of a gas as RT by P, and this is your observed volume of the real gas. Clear about that? This is the volume occupied by the gas in reality, so this is the observed volume, and this is the volume of the gas as it would have occupied if it were ideal. Okay, so this denominator wala volume can now be substituted, so this is for 1 mole. Alright, so it can be substituted. What is your V? It will be equal to RT by P. So RT by P into Vm will give you. So your compressibility factor is basically Z is equal to PVm by RT, where pressure and temperature are the pressure and temperature which are applicable to your ideal gas. Alright, and your R is the universal gas law constant, for which we have done different values last time. Compressibility factor, or it is also known as the compression factor, and it actually is a measure of some kind of deviation from the ideality, कि कितना deviation हो रहा है. So that is like measured in terms of compression factor. And how is it done? It is done by plotting a graph of your compression factor versus P. Alright, it is, okay, if it was an ideal gas, look up onto the board. If it was an ideal gas, then your Vm by Vm ideal will be equal to 1, because then in that case the observed volume will be equal to the Vm of ideal. So if I have to observe it, what does this plot stand for? If this value is like 1 here, 1.0, I start from 0 here. If this value is 1 here, then in that case this graph would be representing your ideal gas. Z for an ideal gas, Z versus P plot will be a straight line which is parallel to your x-axis. Clear to everyone? So now if I talk about real gases, look as to how they behave. What we have is, this is for hydrogen and this is for nitrogen, then you have it for methane, and then you have it for carbon dioxide. Remember that Z is always greater than 1 for hydrogen and helium. Please remember this, put it somewhere, that your compression factor will always be greater than 1 for hydrogen and helium. I will just come to the reason for that. Okay, and it will always be negative for the gases which can be easily liquefied. Like your carbon dioxide can be easily, in fact you have carbon dioxide even in the solid form. So for gases which can be easily liquefied, remember that your Z value will always be less than 1. No, negative, less than 1 doesn't mean negative always. We are now comparing it with the ideal behavior. Okay. So in this case, and another graph that I would like to give you is, this is like for different gases, because each of the gases behave differently. So we have different behavior. This is the behavior of the real gases. So now if I talk about the behavior in terms of temperature, then this is now a question to you. This is for my ideal gas, because ideal gas line should be parallel. Now you have to tell me which of the temperatures is like following what kind of an order, T1, T2, T3, T4. What order will be followed for the temperatures, which will be higher and which will be lower. Alright, you have T1, then we have T2, then we have T3, alright, T3. I am just restricting it to T3 because of my bad drawing. So what we have is, we have T1, T2 and T3. So which temperature is like high? You already know that your real gases will behave ideally at high temperatures and low pressures. So pressure we've already taken care of in this PVM by RT factor. So here whatever temperature is like closer to your line will be the highest, and whichever represents your, see this is some kind of a straight line which is like close to your ideal behavior. So in this case your T1 will be greater than T2 will be greater than T3. जो सबसे ज़्यादा deviate कर रहा है, that will be a temperature which is very low, and the one which represents look similar is the temperature which is high. So this is like common sense. Okay, so I have introduced your compressibility factor here. Remember that for an ideal gas, now some important conclusions from here. For an ideal gas, your Z will always be equal to 1. Z will always be equal to 1, which is independent of temperature and pressure. This will be totally independent of temperature and pressure. And for your real gases, you will always put that Z is a function of temperature as well as pressure. Then I am repeating it again. We have always talked of, till now we have talked of only ideal gas law and ideal gas behavior. Two equations that we've only done which summarizes it all is, one is the ideal gas law equation which is PV is equal to nRT, and the other is the kinetic gas equation which is equal to, now you tell me, PV is equal to 1 by 3 mn u bar square, where u bar is your root mean square speed. Alright, so there, and if I now talk of deviations from ideality, that can be measured by plotting a graph of Vm by Vm ideal. And what is that? That is your Z factor. Z factor is equal to your compressibility factor, which is equal to PVM by RT. Alright, PVM by RT, where Vm is your observed volume and P by RT has been taken up from your ideal gas law equation. So that is the ratio, and we plot a graph between this compression factor versus P, and we see that it does not turn out to be a straight line for any of the gases, which means that none of the gases behave ideally, and if at all they behave ideally, it will be at very, very high temperatures in the low pressure ranges. So from there we get that, and remember that your compressibility factor will depend upon pressure and temperature for the real gases. Now from here, let's talk about the real gases only. What were the problems? There were two major problems with the postulates that we had decided for the kinetic theory. The two that I told you to remember. One was that the volume of the gas is molecule. It's negligible in comparison to the total gas volume. Alright. And the second is that there is no forces of attraction or. Alright. Now here, when I talk about the volume of the gas molecules, in reality they occupy some volume. If that was the case, because the volume of the gas molecules would be similar to the same volume if they are liquefied. But liquid ka to we talk of certain volumes of depending upon the number of molecules that we have. So this assumption was wrong. So we need to introduce some kind of a correction factor in our equation. Some correction factor to my P and some correction factor to my V. So first of all, let's focus on the volume factor. Now what happens is, like you have say some total volume of your gas, because this is your total volume of the ideal gas. Now in reality I am saying that V ideal is equal to, in reality what would happen, this volume would actually be, if they, that means now I am saying they occupy volume and they are interacting, and if they interact, that means they will be interacting with each other by touching each other whenever they interact, and if they are occupying volume, now that volume would also include this excluded volume. I repeat it again. We assume that they do not occupy any volume, which was wrong. Each of the volumes actually is contributing to the total volume. So here what we have is, when two molecules are like interacting, say, or colliding with one another, it is not just the volume of these gaseous molecules, but rather it is also this, because if they will interact, it can be entire volume which will be occupied. बात समझ में आ रही है? अगर वो interact कर रहे हैं, so this molecule can interact in this entire region. What is this space? This is like R plus R, say 2R region. ठीक है, ये it's occupying volume, this is also occupying volume, but we have an extra volume also which is included. So in reality your real gases are occupying more volume than the ideal case. कुछ ऊपर से समझ में आया? In reality your real gases are occupying a volume which is more than the ideal case, because if they interact, there will be an excluded volume which is not taken into consideration before. That excluded volume will be what? What is the volume of the sphere? That is 4 by 3 pi r cube. Alright, and let me just first put it, that excluded volume is my correction factor now. Okay? And that excluded volume is also known as the co-volume. Just remember this. And if that means the ideal volume in comparison to my real volume will be less than the real. So ये मेरा real volume V है. V minus, now I am subtracting that excluded volume from the real. That is what your ideal. Because ideal के case में I did not include the excluded volume. This was excluded. So that is why we call it the excluded volume. This was kind of excluded before. And depending upon the number of moles, or depending upon the number of moles, if this is like for one molecule, then for the n number, for 1 mole, for n number of moles it will be NB factor, right? समझ में आया? So now my V real in reality is more than V ideal, because I have included a factor of excluded volume. ठीक है?
If they are occupying whole of this space, this spherical shell which you have drawn, the second shell of the side में उसका कुछ space excluded होगी तो
नहीं, for each one. Now this is like for one pair. ठीक है, अब या तो ये interact करेगा, ये interact करेगा. I will talk about the interaction again. I will just talk about this entire concept again, because now we are moving from the ideal case to the real. So now here what you have is, this will be like for one pair. Okay, for one pair it will be just that extra volume that we are talking about. What will that be equal to? Say for per molecule, it will be 4 by 3. What is the volume of the sphere? It will be 4 by 3 pi r cube. Here r is your now 2r whole cube. So that will be equal to 8 into 4 by 3 pi r cube. Clear with that?
Yes,
So excluded co-volume per pair, because we are talking about a pair here. The excluded co-volume is equal to 8 into 4 by 3 pi r cube. Now if I talk about, ये per pair है, मतलब for two molecules है. So for one molecule what will it be? So for one molecule it will be half of this. This is for a pair. Okay. And then for one molecule it will be half of 8 into 4 by 3 pi r cube. So that means 4 into 4 by 3 pi r cube, and therefore B per mole, the excluded volume per mole, will be equal to this B per B means the constant that I am talking about. This is my correction term. B per mole will be equal to Na times, क्योंकि ये एक मॉलिक्यूल का है, तो एक मोल में कितने मॉलिक्यूल्स होते हैं? Na, that will be Na into 4 by 3 pi r cube. This entire final expression should be remembered. It's not that difficult to remember. हमने अभी तक ये बोला that the volume of the gas is negligible in comparison to the total volume of the gas. Right? This is what we stated. But in reality, the volume of the gas is significant to us. And if they're interacting with one another, there is some extra volume that is like required per pair. ठीक है? I mean, if this is interacting, then this will move. If this is interacting, then this will move. In both the cases, there is extra volume that is to be taken care of, and that volume factor is nothing but, that is, you can just check up. It will be the radii of the two added up, and that will be equal to the sphere of this extra bigger circle. So extra volume is what? It is your 4 by 3 pi into 2r whole cube, which turns out to be 8 into 4 by 3 pi r cube. This is for one pair because दो molecules हैं. So for one molecule it will be half. This is like we can calculate only for the pair first, and then for one molecule mathematically we've just calculated. If it is for one molecule, then for one mole it will be the Avogadro's multiplied by 8. Okay, and now the volume correction term that has been introduced is like your V ideal is equal to V real minus NB. That means which is more? Real volume is more or ideal volume is more? Real volume is more. B is like the excluded volume or the co-volume. This entire thing is nothing but your B, excluded volume. Exclude हुआ था ये. So another molecule, and you know that all the molecules are identical in size and shape. So that is why we are taking the R and R to be the same. ठीक है? And now when they are interacting, this will be in totality known as your excluded co-volume, which is equal to 4 by 3 pi of 2r cube, and then the entire story again. It is for a pair, and then this is for a molecule, and this is for a mole. So your B is basically your excluded volume. Excluded volume or co-volume, and that value for which is equal to Na into 4 by 3 pi r cube. Why did I segregate? Because 4 by 3 pi r cube is something that you remember. So it is like 4 Na into volume of the sphere. So this is one correction term that is there. Okay, now we move on to the next one. So one correction term is that your V is equal to now V minus NB. The another term is like we talk about no forces of attraction or repulsion, but now we are saying that there is some force of attraction or repulsion. So if at all I have some molecules within which are under same kind of pressure and force from all directions, right? But I may be having some molecules which collide with the walls of the container also. Unka pressure would be like this halfway through. What happens generally? There is some kind of a pressure, which in reality we are saying that there are forces of attraction. Now if there are forces of attraction, the molecules in the center which are more will try and pull the molecules on the side, on one side, as a result of which their velocity or momentum would reduce, and the force with which they generally interact would also reduce, which will reduce the pressure. So the pressure in reality is lower than the ideal pressure. I repeat it again. In reality, we stated that there is no kind of an interaction, no forces of attraction, and perfectly elastic motion. Now we are moving on to real behavior. In reality, होता क्या है? Molecules are moving in your container rapidly and randomly. When they collide with the walls of the container, now here, यहाँ वाला तो is under equal pressure because you have a lot of molecules around, so it is under equal kind of pressure from all directions. So the pressure remains okay. Now the moment you have the pressure exerted from when the molecules collide with the walls of the container, there will be some kind of an attraction. It is only for your understanding that we are talking about. Itna details mein nahi, otherwise you can just directly write down the equation also. Now the molecules which are there on the with the sides or the walls of the container, they will be pulled or attracted by the molecules which are there within. अगर वो उनको pull कर रहा है तो जिस force से उसने interact करना था, why? What is the pressure due to? Due to the collision of the molecules with the walls of the container. तो जिस force से वो interact करता, because of this forces of attraction, it will be pulled by the other molecules, and if it will be pulled back, the momentum would decrease. ठीक है? Because velocity कम हो रही है, velocity कम होगी तो momentum कम होगा. अगर momentum कम हो रहा है तो in one sense the force is reducing, and if force is reducing, that means the pressure is also reduced. So that means that my pressure, that was ideal pressure, that will be equal to the real now pressure, because I will be substituting it, plus some correction term. ठीक है, क्योंकि मेरा real is now less than my ideal. Now this correction term depends upon two factors. One is the number of molecules per unit volume of the vessel. It is equal to, it is dependent upon two factors, that is number of molecules per unit volume of the vessel or container, and another factor is number of molecules which are striking the sides of the container. Number of molecules striking the sides of the vessel. So what is this factor? This is equal to N by V, and this is also, it will be equal to your N by V. So my correction term in this case, say my CT is directly proportional to N by V into N by V, which is N square by V square. And when I remove this proportionality sign, I get a constant A. So I have my P to be equal to A N square, my P ideal to be equal to P real plus A N square by V square. I'll repeat the entire thing again. Okay, so it will be, I repeat it again. There were two, we have done the kinetic theory, you remember all the 7 postulates. I expect you to. Okay, 2 which I told you must be remembered thoroughly. What were those? The very first one was that the volume of the gas is negligible. और हमारे पास ideal gas law equation में ही volume है, तो how can we neglect that? We have PV is equal to nRT. If I talk about 1 mole, so then in that case I have, now look into the small box, PV is equal to RT or nRT रहने देती हूँ. So PV is equal to nRT. Now if the volume is occupied, the volume of the gas is actually, it is important to us, then in that case what volume should be taken into consideration? वहाँ पे we talked of that if two molecules are interacting, then you know that their molecule will be occupying some extra volume. All right, it will be occupying some extra volume which we term as excluded volume. This excluded volume can be calculated from the simple diagram that I had shown to you. This is represented by a factor of B. That means मेरा जो ideal volume था गैस का, ideal गैस का, that I underestimated, क्योंकि reality में it is more than that. So if it was more than that, then my ideal is equal to V real minus N into B, where your B is the excluded volume or the co-volume. This is equal to Na into 4 by 3 pi r cube. You know now how we calculated that. ठीक है? And remember that this B is related to your compressibility factor. Lower the value of B, greater will be the compressibility factor. Please remember that. Questions based on this are asked. In the next class, we will take up very many questions, so all these concepts should be revised by then. B is nothing but it is the compressibility factor. Oh sorry, it is the excluded volume. Compressibility factor is your Z. Alright, B is your excluded co-volume. So then I can simply replace my V ideal now with V minus NB. ठीक है? And your pressure, now for pressure I stated that there is some kind of force of attraction. The pressure of the gas is mainly because of the collision of the molecules with the sides of the container. So you have molecules in the center, ये रहा हमारा container, wall के साथ it is like colliding. Ideally हमने जो भी pressure लिया था उसको कैसे change करें, that we get to know about the real. If the molecule is colliding with the sides, it's resulting in the pressure. What happens is like, now we are saying that there are forces of attraction. Attract कौन करेगा? जो molecules जो major chunk में बीच में हैं, which are moving rapidly, they will try to pull it towards itself. So they will not allow it to interact with the wall as much force as was required. ठीक है? तो वो वाले molecule का speed कम होगा तो momentum will reduce, and if momentum reduces, your force also reduce. Or in short, if it is attracted by the other molecules, the force that it initially would have exerted onto the wall would now be reduced. And if that decreases, your pressure will also decrease. So in reality, your real pressure is lower than that of the ideal one. So that means my ideal pressure is equal to the real pressure plus some correction term, क्योंकि ideal वाला ज़्यादा है, ठीक है? और ये correction term depends now on two factors. One is the number of molecules per unit volume of the vessel, कि कितने molecules हैं per unit volume, and secondly my pressure is also dependent with the collision. So the number of molecules colliding with the walls of the container per unit volume, वो भी same factor ही होगा, because जितने molecules अंदर हैं, every molecule has the probability of colliding, so that is again equal to n by v. So what we have here is that the correction term is equal to n square by, directly proportional to n square by v square. When we remove the proportionality sign, we get a. All a and b, here a and b both are constants which are characteristic for a particular gas. Okay, and remember that a is a measure of forces of attraction, where b can be compared to the compressibility factor. A is a measure of forces of attraction. Larger the volume value of A, all right, say if I give you a question like, if the volume occupied by a particular gas has reduced or is occupying lesser volume, say volume of gas A and volume of gas B, alright. I am taking two gases A and B. I am saying that the volume of gas A is 50% less than the volume of gas B, alright. Now you tell me which option will be correct. A of gas A is greater than A of gas B. A of gas A is greater than B of gas B. Next, A of gas A is less than A of gas B, and fourth, A of gas B of gas A is greater than A of gas B. Remember that A and B are simple constants, and your A is a measure of forces of attraction, B is related to your compressibility factor. It can also be related to your volume as well. Now here when I am talking about the volume of the gas, remember that अगर हमारा A ज़्यादा होगा तो that means greater forces of attraction, and if you have greater forces of attraction that means the volume will be less. So in this case you can say that your A factor, first of all there is no relation between A and B that can be compared. No comparison between a first standard student with a 12th standard student. So the next thing will be your A, that is a measure, will be now for gas A will be greater than that of gas B, which means that there will be greater forces of attraction, which means lesser volume of A. So that is how we relate it to the volume factor. This is for a particular value of B, for B constant. B मतलब excluded volume, इसमें हमने constant रखा. Okay. Right, and so first option is right. So in the next case, if you have to talk about the compressibility, now say for a given gas, I say that the compressibility of gas B is greater than the compressibility of gas A. Then how will you relate it? Remember that lower the value of B, greater is your compressibility. So you can just compare it accordingly. Lower value of B, larger will be the compressibility, and larger value of A, lesser will be the volume, and greater will be the forces of attraction. See, B is again related to your compressibility factor. That means अगर हमारा excluded volume कम है तो इसका मतलब उसका compressibility ज़्यादा है, तभी excluded volume कम है. That means excluded volume कम कब होगा? जब compressibility गैस की ज़्यादा होगी तो वॉल्यूम कम हो जाएगा. तो दैट इज वाई लोअर द वैल्यू ऑफ बी, ग्रेटर विल बी दी, larger will be the compressibility. Okay, so now let's come to the, now look up, this was your ideal gas law equation. Now we've come on to the real one. What is this? P, this was ideal. P is now for ideal and ideal. Now what have we changed this ideal to? This is now become P plus A n square by V square into V minus NB, where P and V are now the pressure of the real gas and volume of the real gas only. Okay, V minus NB is equal to nRT. This equation is known as the van der Waals equation of gas. Alright, this is your van der Waals. W is generally capital, it's the name of the scientist. So van der Waals equation of for real gases. Alright, this is the van der Waals equation for real gases. Now if I talk about this equation for 1 mole, just put it on your own and write it at least once right now. This is not anything that is to be mugged up. You can just remember, because PV is equal to nRT, and what are the two correction terms that you introduce? One to the pressure and other to the volume. Pressure को increase करा दिया by P plus AN square by V square, and volume, so you could have remembered it even otherwise had I told you directly, but it was only to give you an understanding, because excluded co-volume is equal to Na into 4 into the volume of the sphere. So that is to be remembered. I will just come to it now. This is like, this was the question, the same question that was like asked related to it. Now look, write it down for 1 mole of a gas. For 1 mole of a gas it will be P plus, P plus, write it down yourself, P plus A by V square into V minus B is equal to RT. Alright. Now let's look up what happens to the compressibility factor. Now look carefully onto the board, because here only an understanding is required, and then you can get a number of questions from these equations. If you have an understanding, you can tackle almost all the questions. So what you have is, let's check up at low pressures. At low pressures, what can happen? Your B can be ignored because pressure अगर low है, you can actually ignore your B, which is it can be ignored, which is the excluded co-volume. The volume is like low, they will not interact. अगर pressure कम है, so they will just not interact. So B can be ignored here. If you ignore your B, what does your equation becomes equal to? We are talking about the molar volume. Molar volume because we are talking about 1 mole. So you have P plus A by Vm square, ठीक है? Why Vm? Molar volume है, 1 mole है, into Vm is equal to RT. Simple है, ठीक है? अब इस केस में अगर if I take this Vm inside, it becomes PVm plus A by Vm is equal to RT, or I get the expression for what is your Z? PVm by RT is your Z. So let's get that expression. PVm by RT is your Z. So what is your Z? That is equal to PVm by RT. You get that expression and that will be equal to 1 minus A by Vm RT. You will get this expression. I repeat it again. What we have is P plus An square by V square into V minus Nb is equal to nRT is your van der Waals equation. ठीक है? For 1 mole, we have just taken and simplified the expression like this. अगर हम low pressure की बात करें, if in case you have a low pressure, then you will have a negligible B. Why? Because the molecules will not interact. Low pressure means they're just not interacting, so B can be ignored. If B can be ignored, there are still some forces of attraction, तो इसको नहीं ignore कर सकते low pressure में. So what we have is P plus A by Vm square, B ignore कर दिया. Then we've just rearranged this expression to get our compressibility factor. What is your compressibility factor? PVm by RT. उसका expression will be equal to 1 minus A by Vm RT. Now just look here and let's calculate at high pressures as well. Now this is at low pressures. So now you understand what happens at low pressures for generally of the gases. Your Z is now equal to, Z was directly we had plotted it with Rp here. What happens? Our Z is generally 1 minus some factor. And if it is 1 minus some factor, it will go below 1. So for majority of the gases, do you remember? Your Z was like for hydrogen and helium, it was above. I will just come to it. And for the rest of the gases, it was like a little low. It was low, less than 1. So why does it go low at low pressure regions? Now you know the reason, that it decreases with increase of pressure initially. क्योंकि जैसे low था, तो it will always lie below 1 because it is 1 minus some factor. Forget about the rest. Then, now what happens at high pressures? At high pressures, you can now ignore A. At high pressures, what happens? You can ignore this term A by V square. Why? Because अगर pressure बहुत ज़्यादा है, तो volume बहुत ज़्यादा. If your, now what will happen is, if your pressure is very high, in that case we can ignore the forces of attraction term because you're already forcing the molecules to be close enough. Forces of attraction कब होगा? When there is some distance between the molecules. And if the pressure is high, then the forces of attraction factor can be ignored. So in that case, we ignore this A by V square term, and in that case, what happens at high pressures? Now you tell me, at high pressures, what will the mathematical expression reduce to? It will be P into Vm minus B is equal to RT. Again, get the Z term here quickly from here. What will be your Z term equal to? Your Z will be equal to PVm by RT, which will be equal to 1 plus PB by RT. You can just note it down straight away. Your Z will be equal to 1 plus PB by RT. Alright, and now at this particular point, remember that Z will now at high pressure regions. तभी क्या होता है कि low pressure regions में तो, this was the plot that I had drawn for the compressibility factor. Look into this plot. This was the plot that I had drawn. At low pressures, now you know it was 1 minus some factor. So it was actually going down with in the low pressure region. Now what happens the moment you start increasing the pressure, अब pressure बढ़ता जा रहा है इस side पे, the moment you start increasing the pressure, now it becomes some factor which goes on to increase linearly. है तो ये graph y is equal to mx plus c जैसा ही, right? Now in this case what happens is at high pressure regions now the pressure starts increasing linearly, and for hydrogen and helium remember that A is very very small. For hydrogen and helium we do not even want to induce the pressure conditions to ignore. So for that case what generally happens when we ignore the, for this A is very very small, this is like an important question. For hydrogen and helium generally I told you Z will always be greater than 1, that is because your A is very 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 small for hydrogen and helium naturally. So even from the low pressure range it doesn't follow this expression at all. Right from the beginning itself for hydrogen and helium the equation which is applicable is P into Vm minus B is equal to RT, क्योंकि A is already very small. तो pressure चाहे low हो चाहे high हो, it will only follow this equation, because of which your Z will always be 1 plus Pb by RT, and this will be followed. Okay. Now I will talk about the relationship of van der Waals equation with the compressibility factor and behavior of the real gases again. But the range is low. मान लो एक पर्टिकुलर लेवल से आपने शुरू करा तो एट लो प्रेशर्स वी डू नॉट से कि इसी प्रेशर पे अगर प्रेशर 0.001 एटमॉस्फेयर होगा तभी हम कह रहे हैं कि इट विल बिहेव आइडियली. नो, देयर इज अ पर्टिकुलर रेंज जहां तक it will actually behave in this fashion and it is way off from the ideal behavior. All right, now you check out that here I am talking about low pressure and here I am talking about high pressure. Let me just revise this once again for all of you all. All of you all now repeat the van der Waals equation for me. What is it? P plus a n square by v square into v minus nb is equal to nRT. Clear to everyone? Speak up, otherwise you will sleep. ठीक है? Or what you have is, if it is for 1 mole, you can easily take your n to be equal to 1. Now, at low pressures, we are ignoring our B. At high pressures, we are ignoring our A. We are ignoring our A factor. ठीक है? So now, when we talk about low pressure regions, we see that the relationship of compressibility factor turns out to be 1 minus A by Vm by RT. So that is why for real gases, remember, it is because of this relationship. So understand what are the reasons, because these are generally given in the reasoning questions. Understand the reason that in low pressure regions, why will it dip down? It will go down below 1 and decrease with increase of pressure because of your low pressure which ignores your excluded volume. ठीक है? दो reason ये हो गए. तीसरा reason आपका mathematical expression है, which is 1 minus something. There is no need to remember this expression, which is 1 minus some factor which reduces it. Then at high pressure regions, what happens in high pressure regions? Your P, now you are ignoring your A factor, P into Vm minus B is equal to RT, and here Z will be equal to PVm by RT, which will be 1 plus PB by RT. So it will be greater than 1 now, so it will start increasing linearly to go above 1. So the moment it dips down, it will start increasing again to go beyond 1. तभी ultimately सारी gases का it goes above. Now what happens for hydrogen and helium gases? A is already very small. उनका forces of attraction का जो the measure of the forces of attraction which are already there is very very negligible. So right from the lower pressure ranges, it follows only one expression which is P into Vm minus B is equal to RT. So उनके लिए सिर्फ एक ही equation applicable है. In fact, van der Waals equation for hydrogen and helium always remains as P into Vm minus B is equal to RT. Naturally, because hydrogen gas as it is, it has a small size. So it is generally believed that the molecules are so random and rapidly moving far apart from each other that the forces of attractions are already very low. The van der Waals forces are also dependent upon, even if you talk about the van der Waals forces are generally dependent upon the number of electrons also. And you know hydrogen and helium have the lowest number of electrons, so their forces of attraction are very small. See, at low pressure regions, I stated that in low pressure regions we are saying that the molecules will be far apart from each other. If they are far apart from each other, तो वो फिर उतना ही वॉल्यूम होगा जितना is like the total volume of the gas. फिर हम उस excluded volume को लेने की ज़रूरत ही नहीं है, because that excluded volume comes when two molecules are interacting and coming close to one another. So that excluded volume comes into the picture there. तो उसको इग्नोर करा. और फिर यहाँ पे जब हम बात करते हैं at high pressure regions we say that the molecules are already close enough that और attract करने का कोई scope ही नहीं है. High pressure is basically the entire pressure on the volume, and the pressure is always created by increasing the collisions of the molecules with the sides of the container. Interrelated concepts, so intermingled. All right, so so here what we have is that we talk about another equation. Now what happens at low pressure and high pressure regions, sorry, at low pressures and high temperatures? At low pressures and high temperatures, your both A and B factors can be totally ignored, such that your equation turns out to be equal to PVM is equal to nRT. So not just doing that. So low pressure or high pressure discuss kar liya, and you know the compressibility factor, and just go through the plots once as I am rubbing the board. Okay, next remember that there is some equation which is known as your here I can introduce you to one temperature which is known as the Boyle's temperature. Please note down the Boyle's temperature. Boyle's temperature is equal to A by RB. Boyle's temperature is equal to Graham's law of diffusion. You all will repeat it for me in the end. Now Boyle temperature is A by RB. ये actually has been derived from the virial equations. जैसे हमारे पास Van der Waals की equation है ना, Van der Waals equations, जैसे we have Van der Waals equation is applicable to real gases. Similarly we have 2-3 more equations. One is a Berthelot equation, the other is the Dieterich equations, and there is one more which is important, and that is known as the virial equation. Okay. Berthelot equation, Dieterich equation and virial equation. I think I can just quickly put down the expressions for each of these equations on the board. Berthelot equation is P plus n square TCTB, coming to it. So now what we have is Berthelot equation mein what you have is P plus n square A by TV square. See, it's easier to remember those expressions that you derive. So here again you have, normally for the Van der Waals equation you have P plus an square by v square. That is more important to you. जहाँ पे temperature introduce हो गया वो Berthelot equation है. No need to memorize any other equation except your Van der Waals equation. Alright. So this is V minus NB is equal to nRT. This is your Berthelot equation. So Berthelot equation में what is extra? Temperature. जहाँ पे temperature आया वो कौन सी equation है? Berthelot equation. For the next, wherever you have an exponential term introduced, Na by VRT, alright, P into exponential of Na, this is Na by VRT, alright, this is your pressure into V minus NB again is equal to nRT. So now whenever you have an exponential term along with temperature, that is your Dieterich's equation. Dieterich's exponential e to the power x, e to the power minus x, वो वाला exponential. No, I can understand. When you do sciences, you go to some other world. Okay. So then last one, which is the virial equation. It is generally, virial equation talks about the relationship of Z, which is PVM by RT, that is equal to 1 plus B into 1 by Vm plus C into 1 by Vm square plus D into 1 by Vm cube. Okay. Now and again, from here we have derived our Boyle's temperature. ठीक है, अब ये virial equation is giving you some relationship of your compression factor. You know what is your compressibility factor? That is PVM by RT. And in this case, you can easily remember that is equal to 1 plus B by Vm plus C by Vm square plus D by Vm cube and so on. So iska, this goes on. This is your virial equation. It is important क्योंकि इसी इक्वेशन से आपको when you solve this equation you get the boil temperature and इस temperature की खास बात यह है कि at boils temperature your Z versus P line of an ideal gas is tangent to that of the real gas curve, is tangent to the real gas line when pressure approaches 0. This is all I want to tell you for the Boyle's temperature. ठीक है? Okay. Now remember that what now we are talking about is जैसे वैन डर वाल्स ने कुछ निकाला कि ये करेक्शन टर्म है, ये करेक्शन टर्म है, बर्थेलॉट, डाइटरेशी और विरियल ने भी वैसे ही रिलेशंस निकाले because each one of them did their experiments individually, independently. So for whenever you have a temperature factor introduced to a normal van der Waals looking type equation, then it is Berthelot. Whenever you have an exponential, so it is Dieterisches. And your virial equation gives you the relationship of your compression factor, that is equal to 1 plus B by Vm plus C by Vm square and so on. ठीक है, इसमें से हम derive करते हैं अपना boil temperature, and boil temperature has no particular definition, but because it has been arrived at this temperature, what is observed is कि जो real gas का expected behavior है, that is the ideal gas law, ideal gas का तो एक curve है, वो set है, वो वैसा ही होना चाहिए for all the gases. Remember that the ideal gas curve wherever you are drawing, it will be the same for all the gases, because ideal gas law के हिसाब से all the gases behave in a similar fashion. There is no difference in any gas, no bias, but in reality there is a different behavior. So boil temperature, हमें पता है A and B are characteristic of a particular gas. A and B are two van der Waals constant. A और B को हम क्या बोलते हैं? Van der Waals constant, which are characteristic for a particular gas. So the boil temperature will also be different for different gases. और इस temperature पे होता क्या है? The Z versus P line that you have seen, Z versus P से हमें idea लगता है कि कितना deviation है. So the Z versus P line of the ideal gas is tangent to that of your real gas curve. ठीक है? And that too when pressure is approaching your 0. So this is, and now because the question had come up and we have very less time left, I will just quickly tell you that your critical temperature and pressure क्या होता है वो अभी हम बात करेंगे, because in the next class I'll introduce you to a new experiment. It was not put in today's class, but I'll just tell you एक experiment जो Andrews ने किया था. The name of the scientist is Andrews, and he arrived at critical temperature. He came up to the expression of a critical temperature, that is the maximum temperature at which your gas can be liquefied. मतलब उस temperature से ऊपर आपका liquid will just not exist. एक टेम्परेचर तक हम गैस को लाएंगे जहां पे गैस कैन बी इजीली लिक्विफाइड, द वेरी फर्स्ट टेम्परेचर. इसका मतलब है कि उस टेम्परेचर से ऊपर योर लिक्विड विल जस्ट नॉट एग्जिस्ट. सो दैट इज नोन एज क्रिटिकल टेम्परेचर. दिस यू कैन रिमेंबर फॉर द नेक्स्ट क्लास. व्हाट इज योर क्रिटिकल टेम्परेचर? इट इज द टेम्परेचर above which liquid cannot exist, or it is that temperature at which your gases are liquefied. Then what is your critical pressure? Critical pressure is the minimum pressure which is required to liquefy a gas. ठीक है? And what is your critical temperature? The
temperature above which the gases cannot be
liquefied, or you can just relate it to your pressure and volume once you've arrived at your volume and your sorry, what is your critical volume should have been the last question. Critical temperature हो गया. It is a temperature at which your gas can be liquefied or above which your liquid just cannot exist. What is your critical pressure? Critical pressure is minimum pressure required to liquefy a gas. And what is your volume? It is the volume that is occupied by the gas at critical pressure and critical temperature. ठीक है? एक बार pressure और temperature define हो गए तो आपका volume automatically define हो गया. Okay? So now with this, I would just like to start up with the next concept, that is your Maxwell's Maxwell distribution of speeds. मैंने अभी एक concept समझाया था real gases का कि when your gases are moving in rapid motion, they are colliding with one another again and again. and when your molecules are colliding with one another, तो उनका एक ही speed तो रह ही नहीं रहा. The speed will again and again change. So that is why we do not talk of one particular speed, but we talk about some speed which is in a particular range. ठीक है? So supposedly, if my gas molecules are moving in a speed range of u and u plus du, ठीक है? मान लो u is the normal speed और हर बार वो du के speed से change हो रहा है, so it remains in the range of u and u plus du. Alright, then in that case, I can actually give up a relationship. The manner in which the gases are distributed, the fraction of the molecules which are distributed can be given by the relationship dnu is equal to 4 pi n is equal to m upon 2 pi RT whole to the power of 3 by 2 exponential of minus mu square divided by 2 RT whole into u square into du. I will tell you. dnu is the number of molecules, the small fraction, the small number of molecules which are moving with the speed of u and u plus du. Okay? Your n is the total number of molecules, right? And your du is that small range. I've already told you. ठीक है? n is the total number of molecules. m अगर मैं यहाँ पे ले रही हूँ तो it will be the molar mass. ठीक है? If I am taking it to be r, m is the molar mass, so 2 pi RT, alright, m upon 2 pi RT whole to the power of 3 by 2. Remember this expression term and this u square. That is to be remembered. Because if I have to plot the fraction of the molecules which are moving in between the speed of u and u plus du, तो उस case में, because the fraction मतलब कितने out of the total, so then I will have to divide my dnu with the total number of molecules. Fraction कैसे निकालोगे? इतने number of molecules divided by the total number of molecules. And if I have to check up the range, so it will be dnu by du. I am taking du to the other side and I am taking n to the other side. So that is equal to 4 pi into m upon 2 pi RT whole to the power of 3 by 2 exponential of minus mu square by 2 RT into u square into, that's it. ठीक है? So now here I am talking about the Maxwellian distribution. This is also known as the law of distribution of speeds. This is known as the Maxwellian distribution of speeds. Or this is also known as the law of distribution of speeds. So today's class was a lot of theoretical work, and in the next class we'll start out with the numericals, because from here what we get is this u can be talked of as the most probable. Now from here we can actually get a relationship for the most probable speed. Most probable speed का मतलब है कि कितने number of molecules are moving with this particular speed. Most probable मतलब you know that there are different molecules, each one of them is moving independently with different speeds, right? Now when they are moving with different speeds, the maximum number of molecules will be possessing this speed, alright? That is your most probable speed, and we will just talk about it. And if you want, you can just note down that the most probable speed, for remembering for the numericals from for next time, ump will be equal to 2RT by under root of 2RT by m. What was your root mean square speed? Under root of 3RT by m, because PV was equal to 1 by 3 mnu square. So your most probable speed will be equal to under root of 2RT by m. I will briefly explain it next time, but at least remember the expression. And there is another speed that we talk of. जब हम सारे molecules की speed को add up करते हैं, ठीक है? Understand the difference. जब हम सारे molecules की speed को add करते हैं, that divided by the total number of molecules will give me the average speed. That average speed का formula turns out to be equal to 8RT by pi m. 8RT by, that is equal to under root of 8RT by pi m. This is like very important now. We have now talked about three speeds. One is the root mean square speed that we arrived from the kinetic gas equation. What was the kinetic gas equation? PV is equal to 1 by 3 mn u bar square, where u bar is your root mean square speed. What is the expression? Under root of 3RT by m. Repeat it. What is your root mean square speed? Under root of 3RT by m. Now, I have just explained you the meaning of most probable speed, which I have arrived from the Maxwellian distribution of speeds. In the next class, we will start from the Maxwell's distribution of speed only, so that we can discuss the plots quickly and then move ahead with the questions. Right? Now here, in Maxwellian distribution of speeds, you know why there is a range of speeds, because they are colliding constantly with one another. Then we talk of an expression that he is given directly, where you know that your dnu is the number of molecules, the small fraction or the small number of molecules which have the speed between u and u plus du. N is the total number of molecules, m is the molar mass, T is the temperature, R is the universal gas constant, U is now we will get from here as the most probable speed. The most probable speed is kitne number of molecules will be possessing. This is that speed which is possessed by maximum number of molecules. जैसे मान लो all the molecules are moving with 2 meter per second, weird values, 2 meter per second, 4 meter per second, 6 meter per second, 8 meter per second, and the maximum are moving with 5.5 meter per second, then what is your most probable speed? 5.5. Did you get the meaning? So most probable speed is arrived from Maxwellian distribution of speed, and that is equal to under root of 2RT by m. ठीक है? That is your most probable speed. The third speed that we are talking about is your average speed. Average is मतलब सबका जो normal meaning, you have the speed of all the molecules that divided by the total number of molecules, and that is equal to under root of 8RT by pi m. That is equal to 8RT by pi m. Now I am giving you a home assignment. Just find out the ratio of URMS to U most probable to U average. You can find out, this is like a very much hot question for your IIT JAM exam. The ratio of URMS to UMP to U average, that is like checking out the relationship of all of them. You know this is under root of 3RT by m, under root of 2RT by m, this is under root of 8RT by pi m. Okay? And if you have to actually, let me just draw, I told you, this is your expression that will give you the fraction of the molecules moving with the speed of u and in between the speed of u and u plus du. How does the graph look like? यहाँ पे I will take on the y-axis my fraction that is equal to 1 by n dnu by du, alright, and this versus your speed of the molecules. Now this will be like something like this. This is how it goes. I will explain this curve in the next class according to the expression. ठीक है? And the other one is this. This is your T1 and this is your T2. Can you just tell me which will be greater, T1 or T2? Think about it. Okay, now let me just talk about this curve. Let me just talk about a simple curve. पहले क्या हो रहा है? This fraction of molecules moving with a particular speed, जैसे speed बढ़ रही है, that fraction of molecules is increasing. ठीक है? That fraction of molecules is increasing. Now here, after some time it starts decreasing. ठीक है? तो अब एक चीज याद रखना कि initial part of the graph is dominated by your u square factor. तो क्या होता है? जैसे जैसे speed बढ़ रही है, the number of or this fraction is also increasing as per your u square. Increase कर रहा है. Now till this point your u square was like negligibly, your minus sign was such that it was not making your exponential factor go very large. तो उस टाइम तक ये वाला u square उतना ऑपरेटिव नहीं था because your minus sign was again going increasing. Now what happens beyond a particular range of u? Now your exponential factor predominates. ठीक है? जैसे ही exponential factor will predominate, what will happen? Your negative. Now this is exponential of minus some factor, minus u square into something. So there will be an exponential decay. Understood? I repeat it again. The normal curve of this fraction of LHS, which is 1 by n dnu by du versus your speed looks like this. Now initial curve, it increases, this fraction initially increases with increase in u, Why? Because your factor is directly proportional to u square. It is the u square term which is primarily important because your exponential term is small enough. It's not that predominant. After a particular range of u, what happens is exponential term also becomes a little important, because of which there is then an exponential decay. So this is like the plot of the Maxwell distribution of speed that explains the behavior of the total number of molecules. And where will be your UMP? This is the maximum fraction of molecules. This is your maximum in the curve. And what will this be then? UMP. Because the maximum number of fraction of molecules are moving with this particular speed. So that will give you your UMP. And how do you get the maximum? By taking the first derivative and then putting it equal to 0. That is normally what you do in maths. Have you done differentiation? No. So in differentiation normally what you do is you take the first differential, d by dx करते हैं सिर्फ, ठीक है. तो इस केस में d by du करेंगे, ठीक है. फर्स्ट डिफरेंशियल का जो भी एक्सप्रेशन आएगा that will be put to be equal to 0, and from there you get UMP. If you can understand, it's okay. Otherwise, what is your UMP? Under root of 2RT by m. Happy? So, okay, just a quick recap of Maxwell's distribution of speed. Your molecules are not moving with just one speed, they're moving with different speeds that rise within a range of u and u plus du. The expression needs to be gone through at least 4 to 5 times, that is dnu is equal to 4 pi n into m upon 2 pi rt whole to the power of 3 by 2 into exponential of minus mu square by 2 rt into u square into du. ठीक है, हम किस चीज़ को प्लॉट करते हैं? वो फ्रैक्शन ऑफ मॉलिक्यूल्स है, दैट यू कैन अंडरस्टैंड. एंड देन वी प्लॉट, द प्लॉट लुक्स लाइक दिस. You know what dominates in the first half and what dominates in the second half. From here we get the most probable speed. That most probable speed is equal to under root of 2RT by m. Alright, and from there we'll continue in the next class. Alright, thank you.